and directions in both cubic system and also hexagonal. I was not really happy with the explanation of hexagonal system, so I thought we will redo that once again before we go into the actual crystal structure determination using X-ray diffraction, for example. So let's start with that. What we said yesterday is that if it is a cubic or any other system which is not hexagonal, we use a 3 indices system. We call it as HKL, and this is where you H represents to the, let's say, the A axis, and K represents the B axis, and L represents the C axis as far as, let's say, the unit vectors are concerned. For example, if you take this, we know that this is our A, this is our B, and this is our C. So these are the unit vectors in each of the directions. This is the unit vector, this is the unit vector, this is the unit vector, and HKL represent that. So because you have 3 axes orthogonal system, we can easily use a HKL. And when you came to hexagonal, people also thought, let us use a similar orthogonal system, and people tried to use an orthogonal system with one vector like this, one vector like this, and the third vector which is perpendicular to this. So that's where we can call this as A, this as B, and this as C. And again, we can use a HKL system and try to index the whole thing. Whether it is a direction or a plane can be explained completely based on one A, one B, and one C, which is going perpendicular to this. And this is, let us say, the basal plane in a hexagonal. But what people realize there is that if I use this kind of a thing, I find that if I call this as 1, 0, 0 direction, because it is in the direction of A, for example, this is a 1, 0, 0 in a cubic, and this is 0, 1, 0, right? In cubic, we know that this is 1, 0, 0 direction, this is 0, 1, 0 direction. Similarly, if I call this as 1, 0, 0 direction and this as 0, 1, 0 direction, and perpendicular to this, which is the C axis, if I call that as 0, 0, 1 direction, right now I cannot show this because it is perpendicular to this. And if I use that, then automatically you see that this particular direction in a cube is nothing but 1, 1, 0. Because we are going 1 here, and so this is 1, 1, 0. Similarly, in principle, this direction would become 1, 1, 0 for us. If I use these 2 axis system, the 2 A and B, and the C axis perpendicular to this. So in the basal plane, I can see that this particular direction will be 1, 1, 0, and this direction is obviously negative of that. This will be 0, bar 1, 0. There is no problem with this because this is one positive direction, this is one negative direction, and similarly if this is 1, 1, 0, 0, this direction would be bar 1, 0, 0, negative of that, and this direction would be negative of this, and so it will be bar 1, 0. The problem now that we are facing is that we have 6 directions in this basal plane. All of them have the same symmetry. They are all having similar atomic packing. So you have an atom here, 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 you have an atom here. So the atomic packing is similar, the symmetry is similar, but you see that one of the direction, depending on what is the origin, what is the coordinates that I choose, whether I choose this and this as coordinates, this automatically becomes 1, 1, 0. If I choose something else as coordinates, if I choose this and this as coordinates for me, then automatically this becomes 1, 1, 0. So you can see some of them are not having similar indices as this. We have seen in our cubic system that directions which have similar nature will always have similar indices, and we used to call them as family. For example, we call this as family of 1, 0, 0, which basically means this direction and negative of this, the one which is going behind, this direction and the negative of this which is going behind this direction and the negative of this which is going below. All 6 of them will have similar indices because they are similar in nature. But here all 6 of them are similar. I know it very well that they are similar, but they have different indices. They do not have the same type of indices. To avoid this, people thought, let us use a 3 indices inside the basal plane and then one perpendicular to it to avoid this problem. And that is where a new indexing system called, here what people started doing is they started defining each of this vector. For example, this is 1. They call this as A1. Let us say this as A2 and this as A3. So now instead of 2, I have 3 in 1. And obviously I know that this one is not an independent vector as such. It is a combination of these 2 vectors, negative of it. If this is if this is nothing but the resultant of A1 plus A2, so if I call this as A1 plus A2 vector, this will be nothing but minus of A1 plus A2. So A3 is nothing but minus of A1 plus A2. Knowing pretty well that, people said, if I can use this, then I can show that all the directions will have similar indices. How does that come? Just I will try to show you how that comes in a minute. What we have to do is, because there are 3 coordinates in the basal plane, people thought it is easier to understand if I divide this each of them into 3 parts. So what they did is they divided this whole thing into 3 parts. Let me try to be as equal as possible. They should all be equal. Actually, if you carefully do this, this goes and meets here, and this goes and meets here, and similarly this one meets here, this one meets here. Okay, and similarly now if I join this, this one meets here, this one goes through all of them and meets here, this one goes through all of them and meets here, and this one goes through all of them and meets here. So now you have a mesh of the 3 coordinate system, which is A1, A2 and A3, and each of them divided into 3 parts. Now if I want to find out any one of these, for example, I want to know what is the vector A1, and this is the vector corresponding to the indices corresponding to A1, people call it as H, indices corresponding to A2, people call it as K, and indices corresponding to A3, people call it as I. And to as I told you earlier, I is minus of H plus K. Knowing this, now if I want to say what is the indices of this A1 vector, if I want to consider this vector which is starting from this origin and then ending up here, how do I find out in terms of all the 3? If I want to find out in terms of all the 3, what I can do is I can start from here, move in this direction, and then in this direction and in this direction, so that I reach the tip of the vector. If I am doing that, in how much I am moving in each of the directions. So if I look at it, this is, if I put H, K, I and L and look at the amount of movement in each of the direction, this is A3. A3 is our I. So this is negative of A3. I am moving by 1 because I am dividing this into 3 parts. I can consider each part as 1 part. So I am moving in minus 1, right? This is negative direction, minus 1. And this is what direction? This is our A1 direction. A1 is H direction. H direction, how many I am moving? 1 and 2. I am moving by 2. And this is our A2 direction. A2 direction is what? It is K. So in the K direction, I am moving negative in the backwards, because this is my vector. So this is the backwards. So I am moving by -1. And because this whole thing is inside the basal plane, and all these directions are parallel to perpendicular to our this C vector, so obviously in the L they will be 0. So if I put this is nothing but 2 bar 1 bar 1 0. So I can now write here that A1 direction can be represented by 2 bar 1 bar 1 0. I will repeat once again. What we are doing is, we are starting from the origin, reaching the tip of the A1 by moving in all the 3, so that I cover all the 3 indices HKL. So 1 is in the I direction. So you may say, sir, instead of doing this, can I not do this? Even if I do the same thing, you will get the same thing. For example, I have done it earlier like this. Moving in this direction, started here and moved in this direction, moved in this direction, and moved in this direction. Instead of that, now let me start here, move in this direction first. In this direction, I am moving in the A2 in the negative direction. So again, -1 in the A2. A2 is K. K is -1. Then I move in this direction, 2. What is this direction? This is A1 direction. A1 direction, positive direction, I am moving by 2. So that means it is 2. And in this direction, I am moving by 1. And what is this direction? This is A3 direction, negative of it. So again, -1, 0. So you can see again, this is also 2 bar 1 bar 1. So whether I go this way or this way, finally I am arriving at the same indices. Same indices, you can see. So A1 always has this as the vector. Now if I look at A2, let's look at A2. What is A2? A2, to reach A2, which is this. So I have to start from here, reach here. How do I do that? I can do like this, or I can do like this. One of the two. I will choose one of. Just now I have shown that whether you do this way or that way, you will always end up in the same. So let us start one of them. This is, in this direction, I am going 1. This is negative of I. Negative of I means -1 on the I side. And this is positive on 2 on the A2. A2 is K. So 2 positive. And this is 1, which is negative of A1. So in the A1 negative direction I am moving. So this is -1. So you can call it as bar 1, 2, bar 1, 0. So that means my A2 is bar 1, 2, bar 1, 0. And if you carefully observe, this condition is always satisfied. I equal to minus of H plus K. So this is I is minus of H plus K. H plus K, 2 minus 1. It is plus 1, and minus of that is -1. This is I is again -1 plus 2. This is plus 1, minus of that is 1. So now let me take A3. A3 is this. So that means I have to start from here, reach here. You may say, sir, why are you going by roundabout? Why can't I straight away talk about this and call this as something like 0, 0, 1, 0? For example, A3. If I say 0, 0, 1, 0, this condition is not being satisfied. If I simply call this as 1, 0, 0, 0, then this particular condition is not being satisfied. So I cannot simply call this as the way I have done it in cubic 1, 0, 0. I cannot simply call it as 1, 0, 0, 0. And similarly this as 0, 1, 0, 0. We do not. So that is the reason why we do not use this kind of a thing. And instead of straight away going like this, we are going by a roundabout way and moving like this. Either like this or moving like this, like this. So if I choose one of them, for example this one, I am going, again look at this, I am going in the negative of A1, -1. And this one is 2, movement in the positive direction of A3. A3 positive, it is 2. And this one is, which is 1 unit vector in the negative of A2, because this is parallel to A2, but I am moving in the negative direction. So this is -1, 0. So you see bar 1, 2, 0. I can easily show that A3 is bar 1, 2, 0. And again, I confirm whether this is being satisfied or not. Minus 1 plus minus 1 is minus 2. Negative of minus 2 is plus 2. Okay, it is satisfied. And if you carefully look at it, A1, the H part, A1 is the H vector. You know, this vector which has H as a starting. So A1 will have 2 in the H, A2 will have 2 in the K, A3 will have 2 in the I, because they are those vectors. A3 is basically representing the I vector, and A2 is representing the K, and A1 is representing the H. So we can see clearly this is the how. And so this we have done it in the basal plane. Now if I want to consider any vector which is coming into the C axis, we can do the same thing. But this is a way by which we can easily understand the connection. And if you carefully look at it, all three of them now have similar indices. They come out into, we call this as 1, 1, bar 2, 0 family. So we represent it this way. Now you may ask me, sir, you have shown me A1, A2, A3. Can I also show this vector? So let us choose one of these. There are three such vectors. This is also one vector. So let me choose this vector and show what it is. And what that vector is, let us look at it. Again, how do I come? I start from here, move in this direction and move in this direction. I can also do the same thing in this direction also. So if I start in this direction, move in this direction 1, that is what? A2 positive 1. So A2 is K, that is 1. And this is what? This is negative of A3, okay, negative direction, 2 of it. So this is minus 2. And this one is positive in the A1 direction by 1. So this is 1, 1, bar 2, 0. So you can see this is actually negative of A3. So minus of A3 is what? 1, 1, bar 2, 0. This is bar 1, 2, 0. This is 1, 1, bar 2, 0, which is inverse of it. Very clearly I can see this. So if this is bar 1, 2, 0, this will be 1, 1, bar 2, 0. And other two also. For example, I can show that this vector, which is negative of A1, will automatically become bar 2, 1, 1, 0. You can do it for yourself and you will see that this vector will be that. And similarly, this vector, if I show, you will see that vector will be 1, bar 2, 1, 0. That will be nothing but the negative of A2. And you can see carefully, if you look at all of them, all 6 of them have similar indices now. I do not have any problem. So this, I can now call all 6 of them as one family. And that family is what we call this as this family. 1, 1, bar 2, 0 family. You can give anything, but generally people simply call it as 1, 1, bar 2 family. Like this. So this is the advantage of using a 4 indices system where you have a HKIL system rather than simply using a HKL system. If I had used HKL system, you have seen the kind of confusion we got created. We saw that this vector has entirely a different indices when compared to this vector and this vector. And we know pretty well that this vector is similar to these two vectors. There is no difference between these two vectors. But we are forced to give a new index. We called it as 1, 1, 0. And now you don't see that. All 6 of them have entirely similar nature. So this is the advantage of using a 4 indices system, and people have been regularly using, knowing pretty well that I can convert this 4 indices system into a 3 indices system, okay? Because I can know that this and see if I take it, there can be a relation between all of them. So we'll stop with this as far as indices are concerned, and then go into the first part of our what we called it as structure. We so far talked only about what the structure means. Okay, we talked about various crystal systems, we talked about various Bravais lattices, and we also tried to understand why only there are certain number of Bravais lattices, and then we went into how to index various planes and directions in these lattices. We also looked at symmetry, we also talked about point groups and a little bit on the space groups also. And now we want to know, how do I determine this structure? If I say a material like iron has a BCC structure at room temperature and aluminum has an FCC structure at room temperature, can I determine by certain means? So for that, there are ways to find out that it has this structure, it has that structure by using certain diffraction techniques, and one of the most important technique is an X-ray diffraction. To understand the X-ray diffraction, first of all, we need to understand how do X-rays are generated. So let's try to spend a little time on understanding the basic principle behind X-ray generation. We know that X-rays are generated whenever a high energy beam falls onto a particular sample and knocks off an electron from it. Generally, if you look at how the electrons are generated from a material, if you take any high temperature material, for example a tungsten filament or so, heat it to high temperature, you can generate electrons. This we know. We call this as thermionic emission. Of course, now in electron microscopes, people also use what is called field emission. But in most of the X-ray machines, people do not use this field emission. They usually use thermionic emission. So what they do is they take a filament of tungsten and allow the electrons to fall on a sample, which we call it as a target. And once the electrons fall on this, now from this X-rays are generated, and these X-rays are collected through this whole thing, because electrons get scattered away. If you just keep it in an open atmosphere, the whole thing is kept in a vacuum, and this is what is called usually a vacuum tube. And this is what people usually refer to as, let's say, a copper target or iron target or whatever it is, basically because there is a target on which the electrons are falling, and people have a small window in this vacuum tube through which all these X-rays are collected. And these X-rays are allowed to fall onto any sample of our interest to find out the crystal structure. For example, if it is an aluminum sample, I will find out the structure of the aluminum. If it is an iron sample, I can find out the structure of aluminum. So this is the basic principle by which the X-rays are generated. And when the X-rays are being generated, we see that these X-rays that are coming out of this target do have a various wavelengths. And people have seen that if I look at the intensity of the X-rays as a function of lambda, you usually see a kind of a spectrum like this. That means various wavelengths with various intensities. Whenever the X-rays are falling on a sample, and whenever the electrons are falling on the sample, and the electrons interact with the target, this is the target material, and the electrons are falling on this, and these electrons will interact with the target material and are scattering the electrons in this, and as a result you get X-rays of various wavelengths. And this, the smallest wavelength here is usually referred to as lambda SWL, which is called smallest wavelength. SWL is the smallest wavelength, and that is the wavelength that you get generated when all the electrons energy, electron has certain energy, and that energy, if I call it as EV, and EV is equal to h nu, we know, or hc by lambda. So if all the energy, so every electron that is falling here, based on how much of voltage that I am using to generate the electrons, and based on that I have certain energy, and if all the energy of one electron is consumed by one single collision, then you generate a lambda which can be now given as hc by ev. Okay, because lambda equal to hc by ev, and this is what if you look at use all the necessary constants, you will see a relation like this. Lambda is something like a 12,400 divided by v. So as you can see that this lambda, this is what is called the lambda SWL. That means the lambda that is of the waves X-rays that are being generated because of the collision of the electrons on that. If the energy of the electron is completely absorbed in one single collision, then the lambda of the X-ray that comes out will have this value. And as you can see, this lambda is smaller as the voltage increases. So if I increase the voltage, for a given voltage you get a spectrum like this. Then you may ask me, what are these lambdas? These are all the lambdas that you generate when the X-rays that are falling and the electrons that are falling lose their energy in a number of collisions. As the number of collisions increase, for example, this is nothing but the energy, the lambda. If you go far off, you will see after a large number of collisions, if the energy of the electron beam is lost, then it will have very small energy that is coming out. That small energy is represented by a large lambda. Okay, so the X-rays that are coming out will have varied wavelengths. These are all the wavelengths of the X-rays coming out. Depending on how many collisions the electron is losing its energy, you will generate variety of wavelengths. Out of them, the smallest will be the one which satisfies this condition. And of course, you will have a lot of them, and the probability of having this is very small, and that's why the intensity of that is very small. The probability that the electron loses all its energy in one single collision is very, very remote. And as a result, you will see this. And similarly, the probability that the electron loses its energy in infinite collisions, when it is infinite collisions, the energy is zero. When the energy is zero, lambda is infinite. Okay, because you can see lambda is infinite when the number of collisions are very high. So the probability by which the an electron loses all its energy in infinite collisions is also very small, and that's why this particular intensity of a large wavelength is also very small. So you can see the intensity of a smallest wavelength is also very small, the intensity of the largest wavelength is also very small, and somewhere in the middle you will see the probability will be higher. So as a result, you will see that this has a typical nature where you have a kind of a hump here, indicating that the probability of the electron losing in a certain number of collisions is given by the intensity. Intensity gives you the probability of finding that particular X-ray of that particular lambda. Okay, so this is the wavelength, whereas this is the intensity of that particular wavelength, which is nothing but the probability of finding that. Now if I increase the voltage, then lambda SWL decreases. So what happens? You will see a spectrum like this. So that means the lambda SWL decreases, and not only that, the overall intensity of the spectrum increases. That means the probability of finding any particular lambda will be higher because the energy is higher. The incident beam has a higher energy, so the beam X-ray coming out also will have higher energy. So this is what we call it as a white radiation. And this intensity is usually referred to as some constant into I into Z into V to the power 2. So the intensity of the particular white radiation generally is referred, where I is the current and Z is the atomic number of this sample, of this target from which the X-rays are coming out. V is the voltage, it's a square of the voltage. So this is the typical intensity of it. Now if I, what happens if I keep on increasing the voltage? When you keep on, this is for, let us say, for V1, This is for V2, where V2 is greater than V1. Now, if I increase it further to what is called V3, you see that when the voltage is being increased at some level, the energy associated with that voltage, the EV, may be sufficient to knock off an electron from a certain shell. For example, if I am taking a copper target has certain electronic configuration. So it has certain neutrons, okay, nucleus in it, and it has certain electrons in certain orbits. We call this as a K shell, L shell, and M shell, right? So if this energy of this the electrons is sufficient enough to knock off an electron from here, which is nothing but work, the work function we call it. So where the electrons which are coming here can knock off this particular electron from a K shell, let's say. If it has sufficient energy, then what happens is there is a vacancy that is generated here. And once a vacancy is generated here, an electron from a higher shell can fall either from here or from here. And that is when you get, because the energy differences between these shells are quantized, we can get a particular specific wavelengths of radiation, which we call them as characteristic radiation, depending on what is the electron, from which shell it is falling to which shell, and in which material. For example, if I look at this, when an electron falls from L shell to K shell, we call it as K alpha. This is where from L shell, if it falls into a K shell. If an electron falls from M shell to K shell, we call it as K beta. If it is falling from M shell to K shell. So this is how we call it as K alpha, K beta. Sometimes you can also have K alpha 1 and K alpha 2. Because L shell also has two subshells. And depending on from which shell if it is falling, you will be able to see K alpha 1 and K alpha 2. If your resolution is very high, you may be able to see. And these, all of them have different energies. If all of them have different energies, now let me see. If this is K beta, right? This is K beta, this is K alpha. And because K beta has a higher energy, because this energy difference is larger when compared to this energy difference, so you can see that energy of K beta is higher than energy of K alpha. If energy is higher, then the lambda is lower. Lambda of K beta will be lower than lambda of K alpha. So you can see that this will be a K beta and this will be a K alpha. So you can easily see by looking at this, by looking at what is this energy, and we have now standard tables available for each of the element, what kind of energies are available, because we know for the whole periodic table what is the energy differences between L to K and M to K. All these are available with us. And as a result, the moment I see a particular lambda, I can convert this lambda to energy, and from that I can find out whether this is copper K beta or aluminum K beta or molybdenum K beta, whatever it is, or whether it is L alpha, L beta. All those things can be found out by just simply looking at the lambda, because lambda can be converted into the energy. We know that there is a relation between this. So as a result, I can say that this is K alpha. Between these two, I will always know that K beta will have a lower lambda than K alpha. Not only that it will have a lower lambda, the intensity also will be lower. Why intensity is lower? Because the probability of an electron falling from M shell to K shell is lower than the probability of an electron falling from L shell to K shell. Because these two are close by. So as a result, there is a higher probability that the electron falls from L to K rather than M to K. So intensities are always probabilities of finding that particular lambda. As a result, K beta will have a lower intensity, K alpha will have a higher intensity. But you always do get all this. And again, the rest of the white radiation is also there. And people have seen that these particular lambdas are also functions of what particular element that we are talking about. For example, they have found that there is a relation between the frequency of this particular frequency of this particular radiation. Frequency is inversely proportional to the lambda. You know that. So frequency is proportional to, people have shown that there is a relation like this, where C and sigma are two constants and Z is the atomic number. That means the larger the atomic number, the larger the frequency. That means the smaller the wavelength. That means if I am talking about K alpha for aluminium K alpha, and if I compare the let's say platinum K alpha, platinum having a higher atomic number than aluminium, you will always see the K alpha for platinum will be lower than K alpha for aluminium. Like that, I can always see the higher the atomic number for any particular K alpha. I can compare the same thing with K beta also, L alpha also, L beta also. Any one single radiation, if I plot, for example, if I plot K alpha as a function of Z, you will see that it will have a relation like this. If I put all the Z's, the whole periodic table on this axis, x-axis, I can show that the lambda, if this is lambda of K alpha, the lambda of K alpha will keep on decreasing as the atomic number increases. So people have seen such relations, which is like a y equal to mx plus c kind of a relation, that it is a straight line relation between these. So, and from that I can identify what these are. Now the problem that comes is, the X-rays that are coming out have both K alpha and K beta. Sometimes they also have L alpha. Where does the L alpha fall? If I look at L alpha, for example, if this is K, if this is L and this is M, what is L alpha? L alpha means the electron falling from M to L. This is L alpha. And what is this energy? Depending on that, whether the K alpha, this is K alpha. Electron falling from L to K is K alpha. Please remember always the first letter K represents that electron is falling into that shell. Okay? For example, when I put the letter L, that means electron is falling into the L shell, or the electron has been knocked out of the L shell and the electron is falling into the L shell. The alpha, beta, gamma represent, the alpha means the electron falling from the immediate next shell. Beta means it is the electron falling from the next shell, the second shell. And if there is a gamma, then that means it is falling from the third shell. So this is how we can easily recognize what these particular notations mean. K always means electron is falling into the K shell. So if I ask you this question, whether K alpha and lambda of L alpha, which one will be lower, it depends on what is the actual energies. If I know this energy difference, and if I know this energy difference for a given material, I will be able to say that whether this will be lower or this will be lower. Whichever has higher energy, it will have lower lambda. So one can do all those. But what is the problem that we always face is that the X-rays that are coming out of my target, onto which the electrons have fallen, these X-rays that are coming out have both K alpha and K beta inside them. Maybe also L alpha. Okay? And this makes the whole life more difficult. The reason is, now these X-rays, if I am going to use to find out the crystal structure of the particular element such as aluminum, or an alloy such as steel, I want to find out the crystal structure, then I am sending a range of wavelengths into my sample. When I am sending a range of wavelengths into my sample, finding out the crystal structure is a little more difficult. You will know why it is so as you go along a little later when we start understanding the diffraction principles. So what people do is it possible, can I generate what is called monochromatic radiation? Monochromatic means, mono means single. Can I have a radiation with single wavelength? That means I have to somehow make sure that one of these is not there. Okay, either alpha or beta is not there, and I know that alpha has a higher intensity than beta, so I do not want to lose alpha, because my X-rays which are falling on my sample are going to have higher energy. If the X-rays are falling onto my sample with a higher energy, the diffracted beam that is coming out will also have higher energy. So energy of the diffracted beam is always dependent on the energy of this, how intense the particular X-rays is. So as a result, I would like to see that this is cut off, if possible, so that I have only K alpha falling on my sample, so that one single radiation of single wavelength is falling. And how do I do that? And in that connection, people have found that there is some concept which makes this possible. And that concept is called absorption. People have found that when X-rays fall on a sample, they are absorbed. Because of these X-rays interact with the atoms inside the material and get scattered away, and as a result they are absorbed. And as a result, they find that the intensity of the X-rays that are falling on a sample are always related to the intensity of the incident intensity into e power mu of x, where mu is called absorption coefficient. It's a number given the ability of a material to absorb. Each material have different abilities to absorb, and it also depends on the thickness of the sample. For example, if I have X-rays going through a sample which is thinner, and another case it is thicker, so the X-rays that are coming out, if I call this as I naught, if I call this as I, then if this is I naught, if this is I, so the I in this particular case will be lower when compared to this I, because not much is absorbed because this is thin. That's why the thicker sample will absorb more. That's why X comes into picture. This is the X, the thickness of the sample. And people have found that this absorption coefficient is a function of density of this material. Different density materials will absorb differently. As a result, people said, let us normalize it with respect to density, and hence people started using a modified version where you say mu by rho into rho x, where mu by rho is a constant now. It is a fixed, and it is not a function of the density of a material. So as a result, this is a material property which is called mass absorption coefficient. And people usually have certain numbers for each of this. And this mass absorption coefficient, people have found that that itself is a function of the atomic number. If I look at mass absorption coefficient, people have found that it is a function of A into lambda cube into Z cube, where lambda is the wavelength and Z is the atomic number. So if I plot mu by rho as a function of lambda, I see that the mu by rho decreases as the lambda decreases. You can see as the lambda is decreasing, mu by rho is decreasing. What does that mean? If I decrease the lambda, the energy of the X-ray is very high. As the energy of the X-ray is very high, then it does not get absorbed, it comes out. So for example, if I have a sample of a given thickness, same thickness, let's assume this to be same thickness, and I send two beams, one with a certain energy I1, another case I2, where I2 is larger than I1, and that means lambda 2 is smaller than lambda 1. I is higher means lambda is smaller. If I send that, then the energy that is coming out for a given thickness and for a same material is going to be higher. If I2 is higher, the I0, if I call this as I02 for the sake of understanding, then I2 is the energy of the beam, the intensity of the beam that is coming out will be also higher than this. So if I02 is greater than I01, then I2 will also be greater than I1 for the same material, for the same thickness. So as a result, we can always say that this is how if the incident beam has a lower lambda, okay, the absorption will be lower because it does not get absorbed, it gets transmitted. If the incident beam has lower energy, that means higher lambda, it gets absorbed, it does not get transmitted. So as a result, you can see the mu by rho is always a function of lambda. But as you see that as the lambda decreases, keeps on decreasing, then the energy of the lambda increases, and at some stage this energy may be sufficient. If I am sending an X-ray beam on my sample, this may be an aluminum sample, this may be a copper K alpha, and if I am sending a copper K alpha and aluminum, the moment the energy of this is higher than, let us say, the energy that is required to knock off an electron from a K shell, let us say, then this particular electron from here is knocked off. And once the electron is knocked off, there is a lot of energy which is absorbed, because all this energy is consumed to knock off this electron, and as a result the absorption coefficient suddenly increases. So when at a particular characteristic wavelength, until that as the wavelength decreases, the absorption coefficient keeps on decreasing because it gets transmitted. But the moment you reach a particular wavelength where the energy of the electron is sufficient enough to knock off an electron, and this particular energy totally is consumed in knocking off an electron. So as a result, suddenly it increases. And this is what is called K edge for a material. And further down, again it keeps on decreasing. You can see there is always a tendency that as lambda decreases, mu by rho decreases. So this is what is called a K edge. And this comes because when an electron, here we are not talking of electrons, it is, whenever I say lambda, this is lambda of X-ray. When X-rays of a particular lambda are falling on a sample, and as the lambda of the X-rays keeps on decreasing, more and more penetration takes place. As a result, the absorption is low, but once the X-rays have sufficient energy, this is like a secondary X-rays. We have already generated X-rays by pumping electrons onto a sample, onto a target like copper, got X-rays, and these X-rays are falling on another and again generating X-rays. This is what people call it as fluorescence. So we can generate additional X-rays by X-ray beam falling on it. But our intention is not this. We do not want to use copper K alpha to basically generate X-rays out of my aluminum. I want to use it only to find out the crystal structure of aluminum. So I do not want these the X-rays of copper to be completely absorbed in this. I want simply it to be reflected, diffracted, so that I get a diffracted beam. And if this is completely absorbed here, the diffracted beam will have very low intensity. I will not have any intensity. For example, if I look at the copper K alpha has a lambda of 1.54. To be exact, it is 1.541 around. In fact, copper K alpha 1 is 1.5405 to be very exact. But if I am taking an average of K alpha 1 and K alpha 2, it comes out to be somewhere 1.541. And if I look at the K absorption edge of iron K edge is around 1.73. That basically means that if I am sending a copper K alpha is 1.54. So copper K alpha radiation will have a wavelength which is lower than, this is copper K alpha, it is lambda is lower than the KH. So when I am sending an X-ray, let's say I am sending an X-ray of copper K alpha onto an iron sample. Once I send it to an iron sample, now the energy of this copper K alpha is such that it can knock off an electron from the K shell because it has a higher energy. The lambda is lower. The lambda is lower means higher energy is higher. So as a result, it can knock off an electron from the K shell of an iron. And as a result, this is 1.73, let us say, iron KH. And this is 1.54, which is smaller than that. So as a result, all this copper energy is absorbed inside the iron. It is consumed in just knocking off an electron from the K shell of an iron, and as a result, there is no beam that is coming out. The diffracted beam will have almost low energy. And as a result, we rarely use a copper K alpha for determining the crystal structure of iron. This is one of the problems. So you have to choose a proper K alpha for a given material. For example, if you have a steel, you should not use copper K alpha to find out the crystal structure of a steel. Because if I use copper K alpha to find out the crystal structure of steel, all the energy of the copper K alpha is consumed only in that. And if you look at the diffraction pattern, the intensity of the diffracted beams will be very small. You will never be able to see them. They get kind of merged into the background noise. So you look like the whole pattern looks very noisy pattern. You will not be able to see the diffracted peaks at all. So as a result, we have to be careful in choosing. So that's why people choose for iron, either they choose iron K alpha, or cobalt K alpha, or chromium K alpha, things like that, which are all having lambdas which are higher than the KH. You have to use always the lambda which is higher than this. My lambda of my radiation, whatever radiation that I am using, should be on this side rather than on this side. This is the reason why one has to be careful in choosing. Now coming to this problem of, can I take a target such as copper target from which the both K alpha and K beta are coming, and I want to somehow cut off this. To do that, what I do is simply choose a particular thing called filter. For example, copper K alpha is 1.54 and copper K beta is approximately 1.34 or something like that. So what I can do is I can put a KH. So let's say we have a spectrum with K alpha, K beta and K alpha. This is K alpha of copper, K beta of copper. This is approximately 1.54. This is approximately 1.34. And I choose a filter which is a nickel filter, which has a KH around 1.45. So that means what I am doing is my X-rays, copper X-rays are generated, electrons from tungsten filament have fallen on my copper, X-rays are coming out, and these X-rays will go through the window, no doubt, my window of the tube, and they are coming out. Before they fall onto my sample, I put a filter here. And that filter is a nickel filter, let us say. If I put a nickel filter, what happens is copper K beta, the lambda is lower than the nickel KH. That means it has higher energy that is sufficient to knock off the electrons in the K shell of nickel. So as a result, this particular the K beta gets consumed, it gets absorbed by just simply exciting K electrons from the nickel shell. Whereas this, nothing happens to it. Because its lambda is higher, the energy is lower, it cannot knock off an electron from K shell. Though there will be some absorption, because at any given energy there is a small absorption, but it is not a characteristic absorption, it is only a general absorption. So as a result, what happens is when it comes out, the K beta will have very small energy and K alpha will have very large energy. So this is an unfiltered radiation. This is a filtered radiation. After filtering, depending on what does this filtering depend on? As you can see, that intensity is I naught into exponential minus mu by rho into rho x. This is what is our formula. So this much, how much of this intensity gets absorbed depends on this, which is characteristic for nickel, and also this. So if I use a thicker filter, more energy is lost. But at the same time, if I use a thicker filter, even some copper K alpha also will be lost. So I do not want to use too much of a thicker filter, but at the same time, my choice of the filter should be such that the lambda should fall between exactly the K alpha and K beta. So for each of the target, if I am using a chromium target, if I want to cut off the K beta of chromium, I should choose a filter which falls between chromium K beta and chromium K alpha. So I need to know the KH for each of the elements in the whole periodic table, and also I need to know where the K alpha, K beta for each of them. So whenever I want to cut off a K beta, I choose a proper radiation. This is how we can actually do, and finally get one, as far as possible, one single wavelength, and as far as possible cut off this. And you will see a little later, if I have this, what will happen. You will start seeing that the whole XRD pattern, the diffraction pattern, is very clumsy with so many peaks coming out, which you do not understand. We will see why this happens when you have more than one radiation. So this is how we start preparing a beam with a particular radiation, which we usually use it as K alpha. We rarely use L alphas and things like that, because the probability of L alpha and the energies of L alpha are much lower when compared to the K alpha. So most of the time what we use is K alpha. K alpha of different K alphas, depending on which material I am trying to study. For most of the application, copper K alpha is what is used, excepting metals such as iron. If you want to determine, and that is where you have to use either iron K alpha or chromium K alpha and things like that, so that their K alpha is higher, lambda is higher than the KH of that particular element.